Okay, so I think we are ready to move on. Yes, it looks good. So we can move on to flexible bodies. So first I will have a short introduction about how is a flexible bodies and why you should model the flexible bodies. And then we're gonna look at the two methods. We're gonna explain you about the landmass approach, and then I will explain you a little bit about what is a problem about landmass approach. And shortly, it's something that is called numerical stiffness. Numerical stiffness is something that I will ask as an in-class quiz. So this is good to you to keep in mind. So as soon as I start the discussion about the numerical stiffness, make your full attention or put your full attention to me. And then finally, once we're done with that, then we're gonna move on to floating frame reference formulation, and that's where I'm gonna explain the short background about finite element method, or where the finite element method originated from. What's the idea? And shortly speaking, it is all about how to predict the particles between the nodal locations to behave. And we have to have a certain assumption how they behave. And this behavior is typically predicted by using polynomials. How that happens and how that created as something important called shape functions, that I hope you to understand based on my discussion. Okay, but let's get started from the landmass approach, and remind me this because the break was short. It was just 5 minutes, so we should close today at 10 to 4. So then, to make this fair game to you too. All right, so with that, let's get started from the overall description of flexible bodies. You know that there is no such thing like rigid bodies in real life. You cannot go and purchase a rigid body because every single body is a deformable body. So now comes a difficult question then. So if every single body is flexible body or deformable body, should we model all the bodies as a flexible bodies or deformable bodies? And this is a very more complicated question than it originally may seem like. Because actually, the reason to model the deformable bodies or flexible bodies to increase the accuracy of the models. The history of multi-bodies dynamics started such the way that whole method was invented in beginning of late 80s, beginning of 90s, and then all the bodies were rigid. And soon people realized that this assumption of having all the bodies rigid is not very good because it can lead to predictions that are very much against reality. So the accuracy of the models were low. And in order to improve the accuracy, they understood that the deformation plays a significant role and that has to be accounted. Now, this tells you already the reason why you should model bodies as a flexible bodies, to increase accuracy. That's the reason. Then, difficult question is that when flexibility is significant enough that it should be accounted in order to make the reasonable accuracy out from your model. And this is a question that no one can answer. There are attempts to give you rules like if the lowest natural frequency of the body is 1/3 of the frequency of the loading force, then you should model that as a flexible body. There are cases that that's not simply true. Then there are explanations that if you have a slender body, very thin body, then you should model as a flexible body. Sometimes you don't need to do it. Sometimes there may be very thick body, but still experiencing very significant deformation. Then, sometimes people are saying when there is a large force is imposed to the system, then you need to do it. None of these explanations are valid. The only real reason, judgment is based on your engineering knowledge. And this is something that takes a while to develop the engineering knowledge. And you can create a method of your own. So you can, if there is a body that someone is asking whether or not this should be modeled as a flexible body, you can measure it like, oh yeah, you need to be modeled as a flexible body. Or you can figure out whatever you want, because there is no rule to figure that out. Alright, so let's move on with how are the methods. But prior to that, when a body deformation needs to be accounted in a multi-body application, then the choices are when large forces are applied to system, when a natural frequency of the body is low, when a slender structure is considered. There's no general rule to make this decision. Okay, so let me move on to this next. Oh, now we have 27 students. Good number of participants. Okay. Would you like to have a little bit of time to think about this, or is it clear? All clear? So you're good. So okay, let me take a look at this. Okay, let me explain something, and then we'll move back to that in-class quizzes in a minute. This is what I shortly explained to you in the course of simulation of mechatronic machine. You know, flexible multi-body dynamics can be considered as a own discipline. And this own discipline can be divided to two different categories based on amount of deformation. And now, there is a small deformation problems and large deformation problems. And it's very hard to say small and large. You know, where's the difference? Here's the difference. You know, if your strain displacement relationship is nonlinear, then you can describe large deformation. And on the other hand, if you're using linear strain displacement relationship, then you limit it to small deformation. Okay, what it means? This is what I explained to you already, but this is important, so that's why I need to make sure that you understand this. You know, first of all, what is a displacement? Well, displacement is how is relation between my original configuration, which in a case of cantilever beam is a straight configuration like this, and deformed configuration. All right. The displacement tells you how this particular point is moved because of the loading force that is here in the free end. Here, oh my God, this is going to be hard to make a drawing that is clear enough. Let me try. Here, this one here is a displacement called as a U displacement. Deformation due to this force. Deformation, of course, depends where you look at your structure. It's going to be different here. Here, the deformation will be this much. All right? So that's what the deformation is. The difference between the original configuration and deformed configuration. And you can actually express the deformation with respect to length of this body. So it's a function of x. All right? You know that there is a relation, there is a possibility to create strain from the displacement. Strain denoted as that. If this relation is, I don't know how to put it, linear relation, that's when you can capture small deformation only. What it means? Well, it means that if you have this structure, like it is shown here, and you're loading this free end, this free end will stay in the loading line, which is all right if the deformation is small. But if the deformation is large, say that it moves to this point here, the deformation look like this. And you can see that's not what happens in reality. Because in reality, actually what happens is that, you know, the deformation is something like this. And now the difference is that there is an axial movement. And the axial movement requires that the strain displacement relationship is nonlinear. There are methods to account that nonlinearity. We will shortly touch those methods, but the main emphasis will be on small deformation. Okay? So that's how it goes. Small deformation problems only. Now here's an animation. When you look at the animation, it's clear that, this one here accounts the nonlinear deformation. This one here assumes the deformation to be linear. Strain displacement relationship to be linear. Okay? You know that this is sometimes referred as a geometrical nonlinearity because it's introducing geometrical changes, significant geometrical changes to your structure. That's why. Then there is another type of nonlinearity that also can take a place, and that's a material nonlinearity. The relation between the strain and stress could be linear if we're speaking about the small strains, but it becomes nonlinear if you have a plastic deformation. That's what you already know. In multibody dynamics, we typically never ever discuss about material nonlinearity. Only in a certain application of biomechanics this is accounted, but usually is not accounted. Why? Because often if speaking about the steel material, and if you have a permanent plastic deformation, then you have really, really lousy design. You got it? Okay. Why it is lousy design? Because if you have a whatever structure, it should not experience plastic deformation, only very locally, but globally it should not take place, because otherwise it's it looks like bended structure or whatever is the loading direction. Okay, now we're gonna look this first method that you're already familiar with. We're gonna look at this in why this is something that we cannot use in a practical cases, and it is related to computational efficiency. And computational efficiency of this method is low because of something called numerical stiffness. This is not yet time that I will explain it. We'll explain it in a second. Okay, let's first look at this. Do we have a problem in a streaming? We should not. But it looked like the online participants, the online participants are now coming into play. That's how it seems. Okay, let's leave this for a little while. And then let's look at this first method. Now this first method is something that you already know. So it's land mass theory or land mass method, which is very, very simple. It's not in a family of flexible bodies, because these do not need any changes in the kinematics. You just take the original body, which usually have to be a beam-like body, and you divide your beam-like body to number of bodies, rigid bodies. And then what you're going to introduce between these rigid bodies is a stiffness elements that introduce the stiffness to all the 6 degrees of freedom. That's the method in short. Now, what is this numerical stiffness that this method is introducing? Well, now if you look at the frequency content, and now there comes the explanation, now you need to listen to me. Now if you look at the frequency content of this structure, there are low frequencies, which are typically associated to, let me take this off, to, let's say, bending description or bending deformation. If this beam-like structure is bending like this, frequency is fairly low. If speaking about the numbers, it could be, say, 50 hertz or less than that. But it also includes very high frequencies. Where these high frequencies are coming from? Each one of these bodies can move with respect to each other. So it's possible that body that is here in the middle, this one here, is moving axially with respect to its neighboring bodies, axially. So axial deformation. And if you think about that frequency, that's much higher than the frequency associated to bending. You got it? There's no stick here, so it's a little hard to make a demonstration, but there's no stick here. What kind of lecture room is without the stick? Okay. This is another good example. I'm not going to break my pen, but you know, the bending deformation here, I can easily do it. But stretching these, only I can do it because of big muscles. That's right. Big muscles make it happen. But you cannot do it for sure because, yes. Okay, so the same reason. Now, so you need to have a lot of forces to make this stretch to axial. So it's associated with a very high frequency. Now comes the problem. So we have small and high frequencies in the same model. So how that makes your life difficult? Let me explain you why. Now, if we look at the response of this structure, such the way that we can attach this to ground here, and we can load it that, say, random direction. It's going to cause the deformation, bending deformation, but axial deformation too. So now, if you're going to look at the response with respect to time, here's your response. Let's say x this direction, or well, let's put it x this direction and time. The response look like this. All right. But now, if we take a close look to your response, let's say that we take this particular spot here, and let's make it much bigger like this. You will realize that there is a very high frequency here, which may not take place in reality. This may be very artificial because of the modeling technique we have. But numerical integrators are able to identify this. They recognize that, wait a minute, something happens here. So let me tune my time step to figure out what this thing that happens, what that it is. So it actually tunes the time step such the way that this frequency is captured. Why? No reason. Because we don't care about that. We only care about the big picture. But it's not allowing you to do so because it is looking at the details and is not willing to give up the details. So that's numerical stiffness. So, shortly, so if you have a structure where, let's make another drawing, if this is a frequency content. So you have here low frequencies and then very high frequencies. This is where the numerical integration procedures are suffering because they will be stuck because of these high frequencies. And they're tuning the time step to capture that. And we usually don't care about that. So we would be rather focus on this. But integrators are not allowing us to do so. There are some techniques that are tailor-made for this kind of numerically stiff problems. But still, this is always something that is good to try to avoid in a modeling when you're making models. Okay, so with that, let's look. So how is this method? So it's, each one of the, the bodies are considered with respect to each other. So it's even able to describe this nonlinear behavior in a certain level. Okay, examples are here. Here, sometimes, even today, some of the cable-like elements, like here's a cable, is modeled by using this approach. It's very hard to see, but the cable is over here, and soon it becomes more visible. Now you can see it, when the background is more, not as dark as it used to be. Can you see the string effect? Even the string effect, when you introduce more load to axial direction, the transverse vibration becomes higher. It's a string effect that you play guitar. Yeah, that's what you do. This is how you're tuning your guitar, because you make it tighter. What happens then? The frequency goes higher. Oh yeah, yes. I don't play guitar, so I don't know this deal. So then, if you screw it really a lot, then it goes really high. It's called tuning, isn't it? Yeah. Okay. String effect. Okay, so cable-like structures are still modeled like that. This is very old-fashioned, very, very old simulation model. So this is where the beam-like structures are modeled using this approach as well. Okay, but let's move on. Now, computationally, expensive method because it may lead to stiff system, numerically stiff system. In the next, I will ask, what's the numerically stiff system? Can you answer that? Would you like me to repeat it, or you know what it is? Okay. Can be applied mainly to beam-like structures. Material damping user is very simple. We will get back to the damping a little bit later in this course. Easy to implement, easy to use, simple theory. Okay, here's my third in-class quiz of today's lecture. Numerically stiff system means that the system contains low and high frequencies. That the system contains high frequencies. That all bodies are assumed to be rigid. That some bodies are assumed to be flexible. Only one is correct. Which one is correct? Okay, and with that, let's move on to... Okay, now we're done with this in-class quiz. What is your prediction about the success rate? 80. Yeah, I think, this 100% happens once in a lifetime. Once in a lifetime. Once in your lifetime. So this was a really, really big deal for you too. It was me too. You notice that I was crying a little bit. Okay. Very good. Very good. Very good. Really, really good. Oh, I think that only one, I don't know, it's really hard. Maybe two students entered the answer incorrectly. But now, numerically stiff system means. And then let me, where is it now? Here. That the system contains, well, I already mentioned what are the choices. So, as next, we're gonna look at, can I leave this? You already entered your answer. Okay, so then, let's look at the floating frame reference formulas, and that brings us to finite element modeling technique. You want to see the correct answer? Okay. Okay, let's take a look. Okay, seems that some of you are still thinking. Are you expecting me first to say the correct answer and then you enter your answer? Would you like to change your answer? You can't. Okay. So maybe this is a. Oh, now it seems that more. You guys are all done. Is this? I guess that this comes with a sudden delay. I suppose because I don't know. There is a temptation me to say what is the correct answer, but then look at this. So it's like 15 students on. Yes. But that wasn't numerically stiff anymore. That was a string effect, just a string effect. It's called string effect, but not related to numerical stiffness anymore. So a different story. Okay, so let me leave this for a little while and then we'll get back to that after, say, 5 minutes. All right? So we're here. Okay, now floating frame reference formulas. Now the most important observation is that, if we're using body reference coordinate system, and with help of body reference coordinate system we describe the deformation, then it is possible to combine finite element method, which is typically very strong to describe small deformation with respect to certain coordinate system, and multi-body dynamics, which is really strong to describe large translation and large rotations. Now, this method, the floating frame reference method, is actually that. So it's actually doing this combination. And now, unfortunately, I don't have the list of questions, but I need to show those questions to you in the beginning of next lecture. But one of the questions that is often asked is like, why this method is called floating frame of reference formulation, where the name is actually coming from. Shortly, it is coming from the fact that this method, reference coordinate system, is used to describe the deformation. In case of rigid bodies, reference coordinate system is attached to body and it stays where it is originally located with no exception. In case of flexible bodies, it can actually move a little bit with respect to your body. And this is where the floating is coming from. How this is actually possible that it is describing the large translation and large rotation and still moving with respect to body. Very confusing, but that I need to explain to you the modal reduction technique to understand where that is actually coming from. Okay. Now, so the basic idea is that let's use the body reference coordinate system. Let's describe the deformation with respect to body reference coordinate system. And now, then if that is possible, then we can use a finite element method to describe this deformation. And that's exactly what we're going to do. Now, here's how it looks mathematically. So we have description of kinematics in this equation. And in this equation, I have, first of all, translation of body reference coordinate system with respect to global coordinate system. No difference. And then I have here rotation of body reference coordinate system. Body reference coordinate system with respect to global coordinate system. No difference. And then I have here vector u bar 0 that tells me where the particle is originally located at. And then I have here displacement. This displacement I will solve by using finite element method, because otherwise it may be hard to do so. So here is in a nutshell. Kinematics, we add one more component, and that one more component is a vector u bar f. And this vector u bar f, I will solve from finite element method. Because in a finite element method, you know that it's very strong to solve the small deformation with respect to certain coordinate system. This time, it will be that body reference coordinate system. You don't know the finite element method yet, but shortly speaking, it is describing the stiffness or the stiffness properties of the structure with help of stiffness matrix K. And then it actually, when you multiply the stiffness matrix with the stiffness, this is something that this is equal to the external applied forces. That's what we do in a finite element method. So we're taking this stiffness matrix, we invert it, and we substituted that to the left-hand side of the equation to be able to solve, displacements, which are called nodal displacements. This is an information that, with modification, goes here. I'm cutting the corners a little bit because actually the component that is missing here is inertia of the flexible body. So I should also have that there too, but shortly speaking, this is how it goes. Okay, this is where the inertia is included. So I have here inertia, stiffness, and external applied forces. All that in respect to body reference coordinate system. And then I have here multi-body system dynamics that is describing the large translation and large rotations. That's how it goes. These two components have to be coupled together. And they will be coupled together here in inertia description. How it goes, that I will explain you a little later. That will be maybe next Monday. few examples. So this is, I don't seem to have, these animations are not here, so I need to show them a bit later to you. But typically used method to describe the flexibility, very often used, not limited to beam-like structures. And why is that? Because I can model any kind of structure with my finite element method. I can use solid elements, I can use beam elements, I can use cells and plates, I can use whatever I want. Not ever I want, but the structural elements and solid elements I can use. And this is an information that tells me how is a displacement. And that's exactly what I'm after here. Okay? Makes sense? Now, description of deformation. And I'm going to use this next 10-15 minutes about that. So it's a finite element method. So you know why the finite element method is needed? To describe the displacement. Now, the next we're going to look how the finite element method can predict the displacement for you. And now, I know that often finite element method is explained as a nodal locations. As you know, there is a net, and the net is something that consists of these nodal locations. And if this is a beam-like structure, I have one node here, then I have one node here, another node here, and what is between is unknown. It's a big black box. You have no idea what happens between these nodal locations. Sometimes they are explained as springs that are there. Finite element method is all about how to predict particles to behave between these nodal locations. It's very, very essential component of finite element method. And that's how I'm going to explain that to you next. Okay, but big picture of finite element method is this. So it is a method to give an approximate solution. This is, by the way, very important to understand. So it can be correct, but is not necessarily correct. It is approximately method, and its solution getting better and better when you're increasing the number of elements. Typically, this how fast you will get the acceptable solution is called convergence rate. How fast it converges to correct solution. It depends on the case, and it depends on many different things. But important to understand that if you have finite element method, it may be correct, maybe not. And there are some ways to estimate its accuracy, but you need to be careful what you do. Now, method, as title implies, consists of elements. So you have elements that are ingredients of the structure. And you can include these elements together in nodal locations, and that's how you can make these structures that look like a fishnet. So in a plate-like structure is actually very close to fishnet. So that's how it looked like. Now you come and solve the displacement at the nodal location, but still you have full understanding about each one of the particles, even those ones that are not located in the nodal locations. Okay, so that's how it goes. Fairly straightforward method, as you can divide at the smaller structures. It is easy to make easy to do the complete computer implementation of the finite element method. Here's what I would like to explain in how is the finite element method. So I have here a very simple element. This is the simplest possible element. And you may be confused because it's so simple, but let me explain what it is. So it's an element that can only, the element that consists of two nodes. The node number 1 and node number 2. Each one of the nodal location, the node can only have a displacement along the x direction. So this node here can only move back and forth like this. This one here only can move back and forth like this. So it's like a spring. Okay? Spring element. You're still with me? Now, what I would like to do is that I would like to get a prediction about how the particles are moving between these nodal locations. So let me erase this. how is each one of the particles moving. If I'm going to take a hold of this end, I'm moving it here, how the particles that are between the node number 1 and node number 2, how they are behaving. That's the question that where the finite element method is getting started with. This prediction can be carried out by using polynomials. Okay? So now I have a total of 2 degrees of freedom in my system, because 2 nodes, each one of the node has a 1 degree of freedom. So that's total of 2. Now I can make a prediction about how the particles within this element are behaving using polynomial. And in polynomial, I can write it as it is shown here. So I have here a constant polynomial value, and then another polynomial that is x. That's it. That's a finite element method. Now what I'm doing here is that I could use this polynomial expansion and solve my unknowns. Unknowns would be hold on, so what this is doing? No. Okay, let's change the color then. Yes, so the unknowns are A0 and A1. That's it. I could solve that, and that gives me what? Displacement. That's all that I need. Now there is a bit of the problem. A problem is this. What is a physical interpretation of these A1 and A2? Not very clear. So it's not easy to say what they stands for. What is that I should make an interpretation if I get the numerical values for A1 and A0. That's a little difficult. So what I should do then is that I should actually convert this polynomial expansion to be expressed by using nodal displacement. Because nodal displacement makes an awful lot of sense. They are something that we can all understand. Because, if this node here moves 1 meter this direction, we all know what that means. It means 1 meter that direction. So it's clear. All right? So we need to make a trick here. We are not able to deal with the polynomial expansion, but let's modify them a bit. Now let's express this polynomial by using nodal degrees of freedom. That will give me a shape function that tells me how this element is planning to behave. This, by the way, is a decision that every element, somebody has made this decision already in advance, but it tells you quite a bit about how is the performance of your element. All right, you got the idea? Seriously? Because I'm not sure by myself, but maybe this becomes clear soon. Okay, so now, here's my polynomial expansion. This is how it is originally. I'm just expressing that using my unknown polynomials, unknown coefficient, as a separate vector. But if you do this operation, you will see that it's just a little bit of manipulation, nothing else. Clear. Then I will use the information that I have. The only information that I have is that I know where these nodal locations are in my undeformed configuration. My x is equal to 0. If we go back to this slide here, you will see that x here, when x is equal to 0, then you are in this nodal location. And when x is equal to L, then you're in that nodal location. That's it. Okay, so this is when I'm substituting the information regarding the location of the first node, and when I'm substituting the information about the location of my second node. Now the x here is L, so I'm doing my substitution. Now this is something that I can create a relation between nodal displacement and unknown polynomials. You see that that's my relation. This is where I can take these unknown polynomial components and solve them such the way that I will take this matrix, put that in the other side of the equation, and invert it. Right. Now, here how it is. this information I can substitute it back to my original equation, and I can get something that is called shape functions. These shape functions are telling me how particles are moving if I'm introducing displacement to one nodal location, one nodal degrees of freedom. Let me tell you a story. You know, here, this matrix that I'm inverting here is a matrix that is 2 by 2 matrix. All right, clear. I'm sorry that this is a story from the history, but you know, because of my age, these are the only stories that I'm able to tell you. You know, when I was young, okay, and now it's started. So when I was a postdoc, I was a researcher in the University of Illinois at Chicago, UIC, which, you know, where the Dr. Sabana is working. He is the most well-known character in this field. So I was working with him, working under his supervision as a postdoc. And I got an assignment. And the assignment was to create the shape functions for the plate element that consists of 48 degrees of freedom. I still remember this like yesterday. Absolutely no difference. So 48 degrees of freedom. So it's meaning that in order to create the shape functions, this matrix that you're inverting is a size of 48 times 48. Okay, so this was a very special plate element, and you know, I started to work with that, and I made my first polynomial expansion. Everything looked good. I entered all the components to this matrix manually. A lot of work. And then I converted that using symbolic mathematical software. I invert it, and it says singular. Okay. So then I realized, okay, maybe there is a typing mistake. I checked everything. No typing mistake, so its polynomial selection was not the proper one. So I select another set of polynomials and make that 48 times 48 matrix, and then invert it, singular. And I spent 2 months in my life to doing this, day in, day out, getting to office, typing the matrix, singular, and then, you know, over and over again until I developed, you know, some kind of automatic way to try different polynomials. And singular, 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 singular. I saw that sign so many times in my, you know, in my screen that I thought that I'm going to lose my mental health. And then one day, not singular. How'd that happen? By luck. Okay, so horror story about this shape functions. So, all right. So, but now I promised. So what it is? So we have 2 minutes time. Okay. So let me wrap this up. So in my shape functions here, you know, my shape functions are this. You know, is 1 minus x divided by L. This tells you how the particles are moving if you're introducing displacement to your first node. This is a bit confusing, but you can see that is a linear distribution like this. So they are linearly distributed. So they may not be not necessarily linearly distributed, but in this case, they happen to be. If I'm introducing the displacement to second node, they are again linearly distributed like this. So the displacement, it's a bit confusing figure, and all becomes clear when you look at the beam-like structure when the deformation is in transverse direction. But here's the important message. Each one of the particles are still predicted. So I'm not looking at the element as a black box. Quite opposite. I'm predicting how they are behaving. And now in this element, they can behave in 2 different ways. Not more than that. But if I keep on adding the elements, the number of ways the system can deform increases. So okay. So with that, let me get back to this next week. And now comes moment of truth. Here. Still okay, now it is. So we're done. So 50%. What do you say? 50, 50. Oh, 15, 15. Which one it is? 50, 50. Record law. What is this? Okay, so okay, I guess you say that you were confused about the string effect. Oh yeah, I know that. Of course. But you said that it was a bit confusing explanation because of the string effect. So I guess that's why many selected B. D is actually not the solution because we are, or actually, yeah, it's not the solution because there are ways to avoid the stiffness in case of rigid bodies. There are ways to make it happen. And then, because the body cannot deform, there is no frequency associated to that. So it's not infinite. And it's all right if you have high frequencies. If all the frequencies are close to each other, because then you can use something called scaling to solve them efficiently. But if you have one set here, another set here, this difference is what makes them to be stiff. That's what it is. So if they are heavily separated, high and low frequency, if they are far from each other, that's what is hard to deal with. And that's what is called numerically stiff. What was that? Okay. Was there something, my explanation was weird or? Okay. So let's just close this. Okay. So on Monday, I'm going to show you the questions that I can ask. Yeah, let's close it. Okay. Oh, no, I don't want to show this. So now I need to take that off from the recording. So next Monday, I will show you the questions that are associated to flexible bodies. And then let's couple slides about the finite segment method, not much. And then we're looking at the eigenvalue analysis, something that is very interesting, how that is associated to modal reduction. But shortly, finite segment method as it is, we really cannot use it that well in a floating frame reference formulation because it includes too many degrees of freedom. So we need to reduce it. And the way we can reduce it is called modal reduction. Okay, so with that, oh yeah, now it is definitely time to stop. So see you on Monday.